environment. Hello, everyone. Welcome to this live session. Let's see with the audience, if anyone is on YouTube or LinkedIn, can you give us the thumbs up just to make sure that you can listen? I think there's a bit of, from my experience with this system, there is a bit of latency.
Oh, I see.
Yeah. Because otherwise, we are the only ones on the show.
Hopefully
anyone on YouTube and LinkedIn, please thumbs up or a comment or something, just to make sure.
Oh,
yeah, there's someone. Fantastic. We have a thumbs up.
An audience of one.
Yeah.
Great.
Okay, can we have another one?
Can you get 2 thumbs up?
Yeah, we got 2 thumbs up. Yeah, there's another person. Yeah, thank you.
Right.
Thank you. So this is actually fantastic. Yeah, so we are not just the 3 of us plus one other person.
I took a differential geometry course, and it was me and one other person and this professor. We were just like in a basement learning differential geometry. It was very thrilling.
Yeah, I mean,
well, in maths is very
my
common.
grad school class was just so small, but that was the case with like a lot of my classes. After the first year classes that had everyone, like any of the smaller ones were like 5 people.
Yeah, it gets down to 5. Sometimes it just shrinks, and you're like, you don't want to leave the room to like go to the bathroom because it's like there's only one.
It reminded me about this story I read somewhere about Andrew Wiles when he was trying to prove the Fermat last theorem. His student, what's his name, Taylor, he was giving a course.
Richard
and these
Taylor,
things. Yeah, exactly. And the course started to have, I don't know, maybe 20 people or something. And then in the end, it was just Andrew Wiles. So they could actually collaborate.
It shrunk down. They thought it was some elliptic curves course, and then it just like intensity like ratcheted up. Yeah, I mean, there were some seminars, definitely with very few people. The funniest seminar name though, we always had like the list of seminars at universities in Boston, and Harvard would do this seminar called the Trivial Notion Seminar, and it was like the most advanced mathematics you'd ever heard in your life, and it was always just like the weekly Trivial Notion seminar. So there's such
and then you show up there and you say, what is this?
What are the trivial notions? Like, what are we talking about? And you're like, we're talking about derived categories and like T structures, and you're like, oh, cool. Very cool.
It reminds me about a little bit the story of the professor giving an open problem to one of the students they don't know, and then they end up solving it as well.
This is a good technique.
More people.
Yeah. All right, cool. More people are
fantastic.
Showing up.
So let's give it because we have 2 minutes before the 10 past. So let's give it 2 more minutes to see if more people join, and then we'll crack on. Thank you, everyone, for those of you on right now. And thank you for confirming, for giving us thumbs up. We are very happy to we do have an audience.
It's a niche topic.
By the way, feel free to intro yourself, where you are coming from, where you are tuning in from. Yeah, the Bourbakis seminar, someone is commenting. George,
The Bourbakis seminar. Oh, yeah. That's like top secret math.
Only fictional attendees.
Yeah, tu parles français.
Okay, so let me just, before I hand over to our guests, this is a very special session. I will just go through some things. Actually, breaking news for everyone while we wait for more people to join in. It turns out that it's my fault. It turns out that there was a typo on the banner for the talk. So we got this chap He was very, 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 very mad. So I got the phone call here, and I actually at the first I didn't know what he was talking about, and then I realized, yes, he did. We realized that there was a typo. In the end, we sorted it out. So this was the original slide. Obviously featuring the wrong ring, so it's not this ring. So if you are a cryptographer and you were intrigued to join this talk because you saw this very interesting ring, unfortunately you will be disappointed. It's not this ring, unfortunately, but rather this one. So this is the correct ring, and we have our Lord of the Ring, rather looking like Joe Biden. Very happy.
One man, yes.
Yeah, so he's very happy we fixed the ring. So yeah, so well done to everybody. Okay, so let me just now talk in serious before I introduce our special guests, or I let them introduce themselves. I will just briefly mention about the Homotopic Minds program, because our two guests are coming from this program. So this is basically a type of a fellowship, academia to industry transition, only for for mathematicians, that we run as part of quantum formalism with the support of Zyco Group. So the idea is to get PhD or postdoc level mathematicians who might be interested in jumping into industry, and giving them support and some sort of a direction for them to explore possible landing zone in the industry. And this project that you will learn about today is within the context of this thing. We have these two young mathematicians who are interested in cryptography, and they've been working on this on a project related to lattice-based cryptography. Without further ado, I'm going to introduce Jackson Walters, who will be doing the first segment of the talk. So this talk is split in two segments. The first segment will be Jackson Walters. The second one is Thomas Silverman. He does actually have, Thomas, actually, you do have the same name as Thomas Silverman, the author in the literature. Anyone who studied cryptography, you was he your professor, by the way?
Yeah, that's right. Joe Silverman was my PhD advisor. I got my PhD at Brown, and Joe Silverman was indeed my PhD advisor, but we're not related.
So yeah, constantly having to say and no relation.
Yes, exactly.
Yeah. Well, I hope I should have forged it a bit to say, to get more audience, to say, Joe Silverman's grandson will be here with us. Protege, exactly.
Yeah, I mean, Joe has a lot of students. I'm not unique in that one.
Yeah. Okay, so without further ado, I will hand over to Jackson Walters to introduce himself and talk a bit about his segment, his part of the project. And then if you have any questions on the chat, feel free. Ideally, it would be nice to wait until the end of each segment and then ask questions to not disrupt the flow. But yeah, with that, Jackson, the floor is yours.
Cool. Yeah, so I'm Jackson. So I'm a mathematician and a computer programmer. My research in math lately has been focused on the representation theory of the symmetric group over finite fields and number fields. But that kind of led into cryptography, and over the past few months, starting last year, I got really interested in lattice-based encryption and started studying it from the mathematical point of view, and that has led into some more applied aspects. And so that's kind of what I want to tell you about today, this joint work with Thomas on ring LWE is the first thing that I'll talk about, and then Thomas will take it from there. So let me share my screen. Let's see. Okay. So I think you should see it now. We get that nice recursion. Yeah, infinite recursion. And then if we just go full screen, I think we'll do the entire talk backwards. Okay, yeah. So this is ring LWE. So that stands for learning with errors. And so the goal of this talk is to tell you what that means, what those words mean, and give you a sort of brief introduction just to, if you've never seen this before, kind of an overview of what that looks like, what that cryptography scheme looks like, and how you might implement it in computer code. And in particular, the language we chose was Rust. We could have used C++, but typically languages like Python are a little bit higher level, they're a little bit slower. Rust is memory safe, it's very fast, and it's kind of the tool of choice in the cryptography community. So that's the reason for choosing Rust as the implementation language. So the goal of this talk is to kind of get to the point where I can show you the code and you understand what it's doing to do key generation, encryption, and decryption. I want to tell you a little bit, very briefly, about the history of cryptography. Just how do you get to lattice-based methods? Like, where does that come from? In cryptography, there's always hard problems that a crypto system is based on. So I'll just briefly mention a couple of the hard problems that are based on lattices, and that's part of where the name lattice-based cryptography comes from. And what's kind of an interesting aside is that these cryptography schemes, and in particular ring LWE, the one I'll tell you about, is actually a homomorphic encryption scheme. And so we'll just give you an idea of what that means and what you might use a homomorphic encryption scheme for. And then finally, we'll do the implementation in Rust, and I'll mention some federal standards that are very recently coming out related to this type of cryptography. Okay. So cryptography starts in the ancient times. So military commanders would have these sort of like spindles or a wooden cylinder, and you would basically scratch in letters along a belt or a leather strap that was sort of wrapped around the cylinder. And so if you wrote your letters in a straight line and you wrote a bunch of letters all around the belt, then when you unwind it, it would look like just scrambled text. But if you had a cylinder of the right diameter, then you could sort of wrap the belt around it, and you would see you would reveal the message. And so that's the very first example. It's not super hard to break, but at that time, people were not familiar with encryption. So if you just saw scrambled text, it was just scrambled text. And so in mathematics, we would call that a transposition cipher. And so that sort of means that you are taking some text and you are translating the letters to down the line. So you might add 3, so if you had the letter A, you might add 3 to that to get the letter D. And so that would give you a transposition cipher if you did that to every letter. And that particular cipher, that shift by 3, is called a Caesar cipher. I'm not a historian, but I think possibly Caesar used it. I don't know. And then there are more complicated variants of that, called polyalphabetic ciphers, where essentially the key is sort of a word, and then you use the letter in the word to tell you how far to move each letter. So it becomes a little bit more complicated, and you can repeat the key multiple times to give you something like a Vigneri cipher. And this was thought to be unbreakable for a long time. This is a very, it was used quite often, and people thought it was extremely secure. But of course, people eventually broke this cipher. The mechanization of cryptography really happened around World War II, and people started building these rotor machines that could do this stuff mechanically and automatically. And so you have stuff like the Enigma machine coming out during World War II and other related machines. And then, of course, the digital computer comes along in the 50s, 60s, 70s. And eventually you get a standardization called DES, which was a block cipher that used a 56-bit key. And so this was standardized, I believe, by NIST in 1977. And then it didn't take very long, actually, because these keys were so small, these 56-bit keys. They were able to do basically a brute force attack on the key. And I think within, I forget how many years, but within a few years, I think it took about 23 hours to break once they had enough computation power, because computation power is growing exponentially. And so the next, the successor to DES was selected in 2001 through a public competition. This is a symmetric cipher. There's something called an asymmetric public key system, which is what we'll be talking about later today. This is an example of a symmetric cipher, which means that the key used for encryption and decryption is the same. And so this is widely used today. And actually, when we talk about post-quantum cryptography, it's important to distinguish which algorithms are vulnerable and which ones are not. And so the next kind of phase of evolution in cryptography was during the 70s and 80s. There's three mathematicians, Rivest, and you can look up the other two names. I forget what they are at the top of my head, but Rivest is the first one. And these were three mathematicians. And so they developed a public key system based on the difficulty of factoring large numbers. So if you have two numbers, say two prime numbers, and you multiply them together, and they're very, very large, and I ask you, okay, what are their factors? That's a computationally, it's currently believed to be hard. Some people think it's NP intermediate, but there's no classical algorithm known for factoring large integers, which just doesn't exist. And so similarly, you can use elliptic curves. So an elliptic curve is a mathematical object, basically a curve, a projective curve of genus 1, but there's a mathematical structure called a group, and in particular there's an abelian group from the rational points on the curve, and that's a finitely generated abelian group, which means it has a rank. And so basically, you know, if you have one of these curves and let's say it's rank 1, then it looks like the integers more or less, and so in that sense you can add these points on the curve much as you would with the integers, but the actual coordinates on the curve are rational numbers that become extremely complicated as you add them together. So if you have, let's say, a base point on the curve, and then you keep adding it to itself, then that sort of becomes the secret key. If I add it to itself n times, then discovering what that n is very, very difficult. So that's sort of the core of this. And when we say discrete logarithm, if you have a group, that essentially means you are looking for the solution to g to the x, where g is an element of the group, and you're raising it to the x power. And it's like, how do you get back x? So if it was the real numbers, you could just take the logarithm. But in a finite abelian group, in a cyclic group, let's say, that's extremely difficult, if not impossible. And so usually these are over finite fields. And so this is pretty modern. These are very widely used today, this type of crypto system. And so what's interesting is that both of these crypto systems, despite being the most modern, are actually the most vulnerable to attacks with quantum computers. It turns out that AES actually is, I talked to a cybersecurity expert the other day, and he informed me that AES is actually very secure. And in fact, we won't get to this part, but well, I'll mention it at the end, but the NIST standards actually talk about something called a KEM, which is a key encapsulation mechanism. And inside the KEM, they use a symmetric key. So it's an asymmetric system, but there's like a hidden symmetric cipher inside. And I think you can even use AES for that. So this is pretty secure. These, I'm going to tell you how to break these with a quantum computer. So you've probably heard of this very famous algorithm called Shor's algorithm. So I want to give you a clue as to like how would you actually use Shor's algorithm? Like, how does this actually work? Like, how would you factor integers with Shor's algorithm? And so so we start with the encryption method, which is actually quite simple. So to get a ciphertext C, you take an integer and raise it to the e-th power and take it mod n. And so that gives you the ciphertext, just this modular exponentiation. And so if you want to get the message m back, then you would have to somehow invert this process. And so basically we would want to find a modular inverse of e. And here n is, we choose a large semi-prime, so a product of two primes. Okay, so since we're looking at powers of m, that leaves us in the multiplicative group, z mod nz. to the times. So that's a multiplicative group. So that's all the elements that have a GCD of 1 with n. And so, well, how many elements is that? So what's the size of this finite abelian group? And the answer is the Euler-Totient function, which counts the number of elements co-prime to capital N. And since it's a semi-prime, that totient function is actually just q minus 1 times p minus 1. So that's the number of elements co-prime to capital N, and that's the size of this group. And so if you were to know phi of n, then you could use the extended Euclidean algorithm. So that's a pretty simple algorithm you learn in number theory to compute the modular inverse. Let's call that d of E. And once you've got this d, you're pretty much done. So now you can write d times E as 1, and then if you take that ciphertext, which is the encrypted part that you don't know, and you raise it to the dth power, then you're going to get m to the d times E, which is just m to the 1, which is you just recovered your message. So I always wondered about this. I mean, I kind of knew that factoring integers was important, but I didn't quite see the connection. So hopefully that's clear. Yeah, so Shor's algorithm, yes, we've already said this. And so, the essential component is finding the multiplicative order of an integer modulo n. And so when we go into the algorithm, what we want to do, so obviously so the previous slide showed that this factorization was important. So how do we do this factorization? And so we're going to find an element A co-prime to n, so that's not hard to do. So once you have a good A, we want to know the order of A. So we basically just want to solve this simple number theory equation. A to the r is congruent to 1 mod n. And then we can write A to the r minus 1 is congruent to 0 mod n. And if r is even, and we can ensure this is highly probable, and if not, we can try again. So if we have an even r, we can basically do this factorization, this difference of squares. And that's pretty good because that means we've almost factored n, right? We have this product of two numbers that's congruent to 0. So we have a really good chance of finding factors if we just take the GCD of these two products. Since we know that n divides, the product because it's congruent to 0 mod n. So if we just take the GCD, there's probably a factor in there. All right, so here's Shor's algorithm in a nutshell. So how do we actually do this on a quantum computer? So again, our goal is to kind of find this R, like how do we find the period R? All right, so the first step is to create a uniform superposition. So unfortunately, I can't get too deep into quantum computing, but just know that there are states that we can label with integers. And I want you to think of the integers as being in binary, so zeros and ones. And I think there's another quantum formalism course where they'll teach you that those states represent a tensor product, so a finite dimensional Hilbert space. That's a tensor product of capital N states. And so you can think of those states as being like a qubit, which will have an eigenstate of 0 or an eigenstate of 1. And so essentially, by tensoring those together, you get you can represent integers or label your states by integers. And so what we want to do is create a uniform superposition of all those states using Hadamard gates. And then we want to apply modular exponential gates, U, where we're essentially going to raise to the kth power, A. So U is going to be an operator that acts on the states, and it's going to give us A to the k mod n. And so those circuits are actually quite complicated to write down, and it's an interesting task that I am currently working on, how to make those gates parameterized so that they can be applied to larger integers. So the third step is to use the quantum Fourier transform, the QFT, to perform phase estimation, and that'll give us the period R. So I want you to just think of this as we're essentially creating this big superposition over all the integers. This is a remarkable thing, by the way. So if you haven't seen this before, you're sort of representing an exponential number of states using only little n Hadamard gates. So big N here is like 2 to the little n, and you're representing an exponential number of states, and you've only used like a logarithmic number of gates to do that. And so you're representing all of the integers from 0 to n at once, and then you're building this function a to the k mod n. And so what's interesting is this is a periodic function, right? So essentially it's like a sine wave over all these integers. And then if you have a sine wave of different frequencies, then the natural tool to use is the Fourier transform. So in fact, we use the inverse Fourier transform here. I think that should be an inverse Fourier transform. And then there's a final step, which is classical, and you extract the actual period from that information. And so if you haven't seen Shor's algorithm before, this is what the phase estimation part looks like, and this is essentially the core of the algorithm right here. So these are the Hadamard gates. So each one essentially it gives you a mixed state. So if you have like 0, it would go to like 0 plus 1 over root 2, and if I think there's another one that does 0 minus 1 over root 2. So these are mixing gates, and so you basically mix everything together, exponentiate everything, and then search for the period with the inverse QFT. Okay, so that's Shor's algorithm. So this runs in polynomial time on a quantum computer, and so that's problematic for cryptography, right? Because if you can factor integers in polynomial time, then you can break RSA, and that's a security concern because quantum computers are real now, and they're at about 127 qubits, but they're growing exponentially, and within 5 to 10 years, they'll be much bigger, and they'll have thousands of logical qubits, and you will definitely be able to factor, a 512 or 1024 bit number. I mean, 5 to 10 years. Those estimates vary widely, but in some amount of time, you will be able to do this. So ideally for cryptography, we want to find problems that are impossible to solve, even on a quantum computer. And so I'm just going to breeze through this. This is the theoretical computer science background, and I'm not an expert on this topic, but the core computer science problem, the hard problem, analogous to factoring integers, is called the learning with errors problem, or LWE. And so this is a core problem which uses integers mod q, and then it has a ring LWE variant, which uses a mathematical object called a ring. And so it's essentially a set of random linear equations that are perturbed by a small error or noise, and we want to distinguish that from a truly uniform random distribution. So just a brief overview. So given a matrix A, an n by n matrix A over Z mod Q, and a vector B over Z mod Q, or I'm going to say vector, element of a rank M ZQ module. But yeah, so let's just say matrix and vector. And so A is a known random matrix, and S is going to be a secret vector, so this S here. E is a noise vector sampled from a narrow error distribution, and Q is going to be a large modulus, so typically a prime number, not always a prime number, but let's for this just assume Q is prime. I think that's okay. And so the goal is to recover the secret S in this problem, or distinguish AB from a uniformly random sample, and we'd like to know that that instances of this problem are hard in the average case. And one way to do this is through a reduction. So the two kind of key problems, and I'll just mention them again. Not a theoretical computer scientist, but they're based on gap SVP, which is the shortest vector problem. And so that essentially means that in a lattice, you're looking for the shortest vector in a lattice. And I'll tell you what the lattice of the relevant lattice is in a moment. And SIVP is the shortest independent vector problem. So this is sort of like a linear algebra variant. So the key thing I just want to note is that these lattice problems are NP hard in their exact versions and computationally hard in their approximate versions, and that there's no known quantum algorithm for solving those problems. Okay, so this is the famous ring that we mentioned earlier, and I think the typo was totally my fault. I had put this +1 up here. And so the variant of this is ring LWE. And so the ring is actually quite simple. So it's just the integers mod q of x, quotients, an ideal generated by some polynomial. And the polynomial is related to the cyclotomic polynomial x to the n minus 1. But you can't quite use x to the n minus 1. This is insecure, so you have to use x to the n plus 1. And this is called maybe the anti-cyclotomic ring of integers, where essentially x to the n is congruent to -1. And so the problem becomes a variant of GAP SVP called ideal SVP, where essentially this is going to give you a lattice, right? So if we just consider the R upstairs, where we don't quite reduce yet, then this is literally a Z module of rank n. So that's the definition of a lattice. And so we can reduce mod q and we get kind of a sublattice inside of it. But yeah, here I'm just kind of reminding you, this is, we can write an element in this ring. Since it's x to the n plus 1, that means I can reduce anything of degree bigger than n to be of degree less than n. So the dimension of this ring, or the rank of this module, is n. And so everything looks like just like a polynomial, essentially, with coefficients in the integers. And we call Ci, this list of integers, the coefficient vector. And so this ring is isomorphic as a lattice to z to the n, right? And so x to the n plus 1 is an ideal, and elements in R map to elements in this lattice, and the error e of x corresponds to a short vector representing a small perturbation. Yeah, and so ideal lattices inherit the ring structure, so you can, it's a module, so you can multiply by polynomials. Yeah, so solving ring LWE allows efficient recovery of short vectors and ideal lattices. So ring LWE enables recovery of the secret S of x, which corresponds to information about the underlying lattice structure. So yeah, there's a reduction that I won't go through, partly because I'm not that familiar with it. But let's move on to some more practical stuff. So our goal is to implement the ring LWE encryption scheme. So I want to tell you about this encryption scheme. So we're going to choose a large prime P and a large N. And we want N to be a power of 2. Typically, it's going to be 512, 768, or 1024. And then we want a prime such that N divides P minus 1. So I think 512 divides P minus 1 here. I hope so. But there's other primes nearby. So we choose this prime and this N, and then we can construct this ring. So this ring is just basically a polynomial ring, a quotient ring. And so it's a finite ring. It's got P to the capital N elements. It might look like a finite field for a second, this R sub P, but it's not. And that's because this ideal is not maximal. It factors. And so the elements of this ring look like this, right? Again, they just look like polynomials of degree at most n minus 1. All right, so how do we set this up? So the public setup involves the parameters P and N, a moderately large integer K, and we want a notion of like small, like what is a small polynomial? And so for us, that's going to mean ternary polynomials with coefficients of -1, 0, or +1. All right, so we'll talk about Alice and Bob. So Bob is going to create a private public key pair by selecting a small random element S of the ring RP, and then a small random element E1 of RP. And then we're just going to define 2 elements, A and B, which is A times S plus E1. And I might have forgotten A, which is interesting because that actually happened before, like in the notes we were using. But A, I think, is a uniformly random element of R sub P. Yeah, I should have noted that. So we have A and B. So S is the secret. S stands for secret. E stands for ephemeral. So E1 can be discarded. Keep S1 as the secret key and make AB as the public key. So the public key is essentially 2 polynomials. It's a pair of polynomials. Okay, so Alice is going to encrypt a message. So she's going to start with a small random polynomial R, the ephemeral key, and then select a random E2 and E3 elements of RP, and then basically just define two new polynomials. A times R plus E2 is V, and W is B times R plus E3 plus Kn. So we're just adding and multiplying polynomials. And then after she does this, Alice can discard K, E2, and E3, and the ciphertext is a pair of polynomials, V, comma, W. And so, okay, so how does Bob decrypt this message? So he's going to compute X, which is W minus V times his secret key S. He's going to round X to the nearest multiple of K, and the result should be an integer, and then just divide it by K to reveal the message M. So that's it. That's the encryption scheme, or the that's the key generation, encryption, and decryption. So that's essentially the bare bones encryption scheme. And so it turns out, and I'm not going to prove this here, but it turns out that this is a homomorphic encryption scheme. So this is a very powerful technology because it allows operations to be performed on encrypted data. So typically, if you had encrypted data in the past, you wouldn't be able to add or multiply it because the data was completely scrambled. But in this case, because we're working over very structured number theoretic objects like these polynomial rings, you can actually preserve enough structure in the encryption to be able to add and multiply. And so if you were, for example, a financial institution or a bank or a hospital with sensitive data, but you wanted to send your data to a cloud provider, or you just wanted to send it to someone to do machine learning on it, or you wanted to just have anybody operate on that data, but you couldn't reveal the data, then homomorphic encryption is a very appealing option because it lets you do this. And so mathematically, what we're saying is this is a ring homomorphism. So the ciphertext space and the plain text message space are rings, and the map that encrypts from the plain text message space to the ciphertext space is a ring homomorphism. And so that means if I add two elements, then their encrypted versions I can add, or if I multiply two elements and then encrypt, that's the same as multiplying their encrypted versions. So this can be used in cloud computing, privacy preserving machine learning, and secure multi-party communications. Okay, so now to the real stuff. So what does this look like in Rust code? So my collaborator Thomas and I have created this GitHub organization, and we've got a couple bare bones implementations of Ring LWE and Module LWE that we've been working on that are open source under an MIT license right now. So a very, very permissive license on this code. And as we develop other tools like the number theoretic transform, we've also open sourced those as well. And those are Rust crates that are publicly available. So the code is available at github.com/lattice-based cryptography. So I'm just going to show you the code. So this is these are the library functions. So like if you want to actually implement this, then you need some notion of polynomial. So we just use a standard crate that does polynomials. There's different notions of randomness that we use that I'll talk about a little, but they're pretty straightforward. It's either uniform, normal, or we also need, these are like distribution is just for the, but really so two distributions, the normal distribution and the uniform distribution. We use the number theoretic transform, which is a number theory version of the fast Fourier transform, and that allows us to multiply polynomials very quickly I'll talk about it later, but just much faster than usual, and then just some randomness that we import. So what are the parameters? The parameters I think we've upped quite a bit, but these are some kind of default parameters to set n, the modulus, and this is what we would call the plain text modulus. And then, you can instantiate polynomials with just using vectors. So here we're just setting the 0 coefficient to 1 and the nth coefficient to 1. So this just represents the polynomial x to the n plus 1. So it doesn't look like it, but that is f is x to the n plus 1. And so that's our polynomial modulus. And so that's the entire set of parameters for this scheme. Yeah, so the NTT, so this is a way to speed up polynomial multiplication. And so it literally looks like a Fourier transform. You're just taking a root of unity. So in the usual Fourier transform, you pick an nth root of unity, and then you just sum over n in this case, just powers of omega. But in this case, I don't know how standard this is, but I like to think of finite fields as circles. So what I mean by that is that the multiplicative group of a finite field is cyclic of order p-1. And so essentially we're just finding a capital nth root of unity. And so it's very analogous to the Fourier transform. And so there's a way to basically split these arrays in half and use the divide and conquer method. And we do this to get a fast NTT. So the algorithmic complexity is order n log n rather than n squared. So it's much faster. So that's what this looks like in code. So we do some splitting of the arrays, and then we compute the modular multiplication, the modular exponentiation, and we have omega, which is our, we have to compute that elsewhere, but that's a capital nth root of unity in the finite field. So this is just the fast polynomial multiplication, just basically uses the number theoretic transform on the padded coefficients. So you have to be a bit careful about the padding. So we talked about this earlier. So the key generation, it's really only like 10 lines of code once you import everything. So we do have a library of multiplying polynomials, adding polynomials, taking the inverse of polynomials, and generating random polynomials. The real key point here is that we want A to be uniform. So you could generate a normal polynomial with a sigma, so some standard deviation. And so if sigma is relatively small, then essentially you're going to get something similar to a ternary polynomial, and you really want to spread that out for A. So in order for security, you need A to be a uniform polynomial. So we were able to get that. And then the rest of this is polyadd and polymul. So we're just multiplying and adding polynomials. And keep in mind, Rust is very, I mean, the memory safety, it's very picky about borrows. So you just need to be careful and pass everything by reference typically, rather than using like clones and stuff like that. So the encryption, again, very short. So we're just doing what we talked about earlier. In this case, we're generating normal polynomials, and I think the current version of the code does include a sigma, so you can specify the standard deviation. But yeah, we generate random polynomials and then essentially do our additions and multiplications and return the ciphertext. So here of note, the public key is 2 polynomials, which, they're generated here. So this would be the public key, B comma A, and then the secret key. So we take that in for encrypt with the parameters and the message, which is typically a polynomial in binary. And then the decryption step, again, just implementing what we talked about before, where we are scaling this polynomial, we're adding this polynomial and multiplying the ciphertext by the secret key and adding it to the other ciphertext. So decrypt takes in just the secret key, the ciphertext, and the parameters, and through this process, we're able to decrypt this message. And so we're still kind of getting into the depths of this, but when you do homomorphic encryption in real life, there's a lot of noise in the homomorphic products. So like it doesn't just mean that you can take as many products as you want and still have it be homomorphic. You're actually going to get washed out by noise the more products you do. And so in order to correct this, we've done this sort of first approximation of this correction. And so that's called relinearization. And so one of our tests, we ensure that we are getting homomorphic products, but we have to use a modified sort of decrypt method, basically, where we are decrypting by using sort of this perturbative powers of the secret key. So it's like s to the 0, s to the 1, s squared. And you have to also be careful that you're doing these additions and multiplications over a ring that is sort of, that allows your coefficients to be big enough. So we actually had to work over q squared rather than q to get this to work. But I think in theory you could work over z, and that would work too. Your coefficients would just get very large. And so with this though, it does work, and you do get the correct homomorphic decryption. So this relinearization process would actually get more complicated as you go to higher order products, and that theory is called leveled homomorphic encryption. So here's that test. So this is basically this equation in code where we are decrypting the product here, and you can see we're working over q squared rather than q, and then otherwise we're just computing these different products of u and v here and kind of putting everything back together. Cool. And so once we got everything working, we have started benchmarking the code. We still need to benchmark the actual keygen encryption and decryption, but importantly, we did benchmark the fast polynomial multiplication. So using the number theoretic transform, we're able to multiply polynomials in 785 microseconds versus the slow way, which takes 4.24 milliseconds. So it's over 5 times faster, which is awesome. So that's a nice speed up. And as we continue to write this code, we're going to make sure that we are benchmarking it to ensure that it's performant and in line with what would be considered standard. Speaking of standards, so NIST released their post-quantum cryptography standards in August. So this is a major competition to decide what the next cryptography standard would be in the United States. And it turned out that a variant of Ring LWE actually won. And so that's called Crystal's Kyber. And they used a variation of this, what I would call a PKE, a public key encryption system. This is what I was talking about before. This is a KEM. So this is a key encapsulation mechanism. And the core of that is actually module LWE, which is what my collaborator Thomas is going to talk about, where instead of using rings, we use modules. So we actually take this ring and take K copies of it to get a module. And that system, you can see this at PQ Crystals. I think they have a GitHub repository as well. So thank you. So I have a blog post about some quantum computing stuff. Catherine Stange has some really great Ring LWE notes. And this is just the link to Thomas and my GitHub repository. Thank you. Okay.
Okay. Well, that was a very, very, very nice talk. I don't know, maybe to not disrupt the flow, just for people to think, maybe we should proceed with Thomas, and then at the end we look at the questions.
What do you reckon? Okay, that sounds fun.
So it's up to you guys. Yeah.
Yeah. Sorry, I didn't realize how long I went. I thought it was like.
Yeah. No. It was all right to give people the background and the thing. Yeah. So yeah. So I'll hand over to Thomas. Thomas, please. Okay. The floor is yours.
Sounds good. Share my screen. Okay, that's working. All right. So I'm Thomas Silverman. Like I said, I did my PhD at Brown. The did not work on cryptography. I did arithmetic dynamics, mostly non-Archimedean dynamics. So this is like sort of like complex dynamics, but doing it over the p-adic numbers instead. Anyway, but I did learn a little bit about cryptography from my advisor, Joe Silverman, back when I was at Brown. He created the Entry system, which is another lattice-based crypto system with 2 other Brown professors, Jill Pfeiffer and Jeff Hostein. So, all right. So yeah, I'm going to talk about module LWE, which, as Jackson said, is a generalization of ring LWE, but you use module R to the K instead of just this polynomial ring R sub Q. So this is a rank K free module, essentially just like a K-dimensional vector space, but instead of a field, you have this module R sub Q, which again is a polynomial ring. And so the elements will just be K tuples of the same polynomials we were using in ring LWE. And yeah, it's a generalization because if you just take K equal to 1, then that'll just be literally ring LWE. All right. Oops. So yeah, if you notice, modular LWE is sort of like a hybrid between the original LWE scheme, which is like vector spaces and matrices just over ZQ, and ring LWE. So you have both matrices and vectors, and also you have polynomial multiplication. All right. So the advantages of module LWE. So a good one is scalability. So in ring LWE, the main way to increase security is to increase the polynomial modulus degree. So the n in x to the n plus 1 is to make that increase. That needs to be a power of 2. Well, I guess needs to be is a strong word, but you want it to be a power of 2 because that's what lets you use the number theoretic transform, the divide and conquer algorithms. To get those to work really well, you want it to be a power of 2, so you can split things in 2 and then split each of those in 2 and so on. So that means if you want to make a small increase in security, you're kind of out of luck. If you're like very close to the level of security that you want, but not quite there, you'll need to double n. You need to multiply n by 2 is the smallest increase you can make. On the other hand, in module LWE, you have this module rank K, and that can be basically whatever you want. So any integer is fine. So if you want to make a small increase in security, you can just increase K. Another thing is, if you don't have to change n at all, if you can just leave it somewhere pretty nice, and then scale the security by increasing or decreasing K, then you can hard code a whole bunch of stuff, especially in the number theoretic transform. So you needed like a root of unity omega. And so you can just pre-calculate all this stuff. So you can find you can pick a prime that works really well for the particular n that you have. You can find a generator for the multiplicative group modulo that prime, and then you can use that to calculate the root of unity that you need. And so you can pre-calculate all of this stuff and just leave it there. And then whatever changes you want to make in the security, you can just use K for that. So for that reason, that all works pretty well. Another reason is that you're doing a lot of matrix computation, so you can use parallelization really easily. We have not done this in our code, but certainly you can very easily do a lot of your matrix operations using parallelized algorithms. All right. So those are the 2 big advantages of using module LWE as opposed to ring LWE. Okay, here's a diagram. So essentially, the scheme works pretty similar to ring LWE. This is the same kind of scheme where you have asymmetric keys. So you have a key generation. You pass along your public key. Bob passes along his public key to Alice, and then she can use that to encrypt, send the ciphertext back to Bob, and then Bob can decrypt. And you're using the same kind of thing. You need to have some kind of uniformly random chosen thing as part of your public key. There's an ephemeral key. There are random errors chosen, but in this case, some of them are polynomials, and some of them will be elements of this module R to the K. And I guess A is a matrix. A K by K matrix. Okay, well, I'll talk about that individually now. So the public setup, you want to pick out your prime Q, your modulus degree n, which will be a power of 2, which will give you the same ring R sub Q that we used in ring LWE. But now you also need to pick your module rank K, and that can, again, just be any positive integer. No big deal. And then finally, a notion of small. So yeah, you can either use like a normal distribution with a small sigma, or you can do something like ternary polynomials. I think in our code, we're just using ternary polynomials for small at the moment, but we have the option to use a normal distribution if we want. So these will be, so each element of a small like this will be a k-tuple of ternary polynomials. So it's a k-tuple, and then each element of the k-tuple is a polynomial in R sub q. And so each of the coefficients of those polynomials will be chosen either -1, 0, or 1. All right, so yeah, so you have n coefficients in each polynomial in the k-tuple. So it's like n times k things. All right, so now key generation, it works pretty similarly. So first Bob will select a small random element as his secret key. That's this S0, and this will be an element of the module R sub q to the k. And since we're going to be doing some dot products, I guess we're using this bracket notation. So this will be a column vector S sub 0. And then Bob will also select a small random element E0. So this is an error element of the module. So it's the error in learning with errors is you're adding small errors to make it that you can't just use, like in the original scheme, you have like, if you just had like A times S in the original learning with error scheme, you can just sort of use Gaussian elimination to solve it. And so you have to add these small perturbations, these small error elements to get you away from something systematic like that. All right. And now Bob will select a uniform element. So this is part of the public key, which will be this matrix A. So this is a k by k matrix of polynomials, and each coefficient of the polynomial will be chosen uniformly at random between 0 and q minus 1. All right, and then finally, Bob will define the other element of his public key as A times S0. So this is a matrix, a k by k matrix times this column vector, which will give you a column vector. And then you add on this random error column vector E sub 0. All right. And you don't need the error element. You don't need to keep track of that anymore. And then Bob will keep S0 as a secret key and then send along A comma P0 as his public key. Okay. So for Alice, so you can start with a message. I guess this can either just be a single bit, or you can take a whole polynomial with coefficients in Z mod 2Z, at least in the code as we have it now. For ring LWE, we had a ciphertext modulus, which could just be any element T, which I think we had as 512 there. But for the module LWE, we just coded it for binary. I think it's pretty standard to use binary regardless. Okay. So yeah, you can either start with just a single bit, or you can take a polynomial in Z mod 2Z adjoint x modulo x to the n plus 1. All right, so you start with a small random element S1, and now this is a row vector. That's why it's using a bra instead of a ket. So it's a row vector in the module R to the Q to the 1 times K. That'll be the ephemeral key. She also will select a error element of the module. I guess 2 error elements in this case. So there's an error element in the module, E sub 1, and then also an error element, which is just a polynomial. So both of these will be small in that sense. And then to get the ciphertext, you'll do a matrix multiplication, S1 times the matrix A, which was part of the public key, and then you add on this error row vector. And then the other element of the ciphertext will be a polynomial. So first you scale the message, right? The message originally had binary coefficients, but if you multiply by q divided by 2, rounded to the nearest integer, now you have something that's sort of scaled up to live in Z mod QZ. Live in the polynomial ring with Z mod QZ coefficients. So you multiply that by your message to scale it up. You add on the error polynomial, and then you add on this dot product S1 dotted with P0. So it's a row vector times a column vector. So you can think of that as a dot product. All right, you don't need S1, E1, or E anymore, and you can send along C and P1 as the ciphertext. And then finally, there's the decryption step. And so how you do that is you take the ciphertext C, and then you subtract the dot product of the other ciphertext element P1 with the secret key S0. All right, then you can divide by this half Q number, Q divided by 2 rounded to the nearest integer. And then after that, you can round all the coefficients to the nearest integer modulo 2, and you'll get back your message polynomial, which had coefficients in Z mod 2Z. All right, to check that this is correct, you can do this computation. So X is C minus P1 dotted with S0. And C from the previous slide is Q over 2 times M plus E plus the dot product of S1 and P0. So that's C. And then P1 from the previous slide is S1 times A plus E1. So you'll have that dotted with S0. And expanding that out, this is using that P0 is A times S0 plus E0. So expanding out that dot product, you'll get this. And then expanding the other term, you have minus S1A times S0 minus E1 times S0. And so the important part is that the big matrix product cancels out. So the S1 times A times S0 has a plus and a minus, and those cancel out. And then what you're left with is Q over 2 times M plus all these small error polynomials, right? So E was a small polynomial, E0, E1, S0, and S1 are all small. So these dot products, S1 dotted with E0 and E1 dotted with S0 are also small polynomials. And so finally, if you divide by Q over 2, you'll end up with the message plus a bunch of small polynomials with their coefficients being divided by Q over 2. And if you round to the nearest integer, mod 2, you'll get rid of these small polynomial terms, and you'll just be left with that. All right. So that's why this encryption scheme works. And so now here's how we implemented it in Rust. So in this case, we're using a lot of similar stuff as ring WE. And in fact, we're using a bunch of functions that showed up in ring LWE. So this is just importing a lot of the library functions from our ring LWE library straight up. So polyadd, polymul, and generating random polynomials. Yeah, I guess we haven't added it yet, but like the number theoretic transform, the fast polynomial multiplication, we'll also add in here once we have that all straightened out. So just like in ring LWE, you'll need to generate some parameters. So in this case, we have n is 32, q is this, and then we have k equal to 8. So you can scale k to get better security. And yeah, in this case, you can use a much smaller n than you would need to in ring LWE. So for ring LWE, you'd probably need n to be like at least 512 for good security. But in this case, as long as you can increase k, you can leave n as a smaller value, which is nice. And again, lets you hard code a lot of the number theoretic transform implementation stuff. And then you can just adjust k. All right, so some more library functions, right? So we needed a dot product and some kind of matrix multiplication for this modulo LWE scheme. In this case, we haven't implemented any like particularly clever algorithms for this stuff yet. So this is just literally just multiplying the coefficients and adding them all up for the dot product. And then for the matrix product, we'll just do a bunch of, so this is multiplying a k by k matrix by a k by 1 column vector is the only matrix multiplication you really need for this scheme. And so in this case, we're just doing a bunch of, you can think of a matrix product as a bunch of dot products. And so that's all we've implemented for now. But yeah, certainly you can do much better matrix algorithms. You can do divide and conquer stuff. You can do a lot of other stuff. You can parallelize things, but we haven't gotten around to that yet. All right. Oh yeah, and in the dot product, right, we're using the polymultiplication, the polymul function from ring LWE. So this is using the same polynomial multiplication mod q modulo x to the n plus 1 that we had implemented there. All right, so here's the key generation. So again, A is a uniform matrix that we're generating, and then the secret key and the error key are both small elements of the K module. And then T is just this matrix multiplication, A times the secret key plus this, this error vector. All right, and then the encryption. Right, we have this half Q element, which is Q divided by 2 rounded to the nearest integer. We have this ephemeral key R, which is a small vector, and E1 is a small vector, and then E2 is a small polynomial, which here, yeah, we had it as a small vector, but it's with K equal to 1, so that's just a single polynomial. All right. And then you can compute. Yeah, so here in the slide I had earlier, I think I had the ephemeral key multiplying the matrix on the left. But since I've only implemented like a k by k matrix times a column vector, as opposed to like a 1 by k row vector on the left multiplying a k by k matrix, instead you can do the transpose of the matrix A times the column vector version of the ephemeral key on the right. And it works out to be the same thing. All right, and then for the other element of the ciphertext, we have this dot product of the public key dotted with this ephemeral key. You add on this error polynomial and then subtract the message. And this is with, oh yeah, this is the scaled message. So it's the original binary polynomial and then multiplied by this half Q element, Q divided by 2 rounded to the nearest integer, to scale it up to be an element of RQ. Okay, and then we have the decryption. So that's, you take one element of the ciphertext, subtract the dot product of the secret key with the other element of the ciphertext. Then you divide by this half Q element, round to the nearest integer, and look modulo 2. And that will return the original message. Okay, and then for module LWE, you don't have a homomorphic multiplication because this R to the K module, since it's like a vector space, you can't multiply 2 vectors to get another vector like that, right? So you can multiply 2 polynomials to get another polynomial, but you can't really multiply 2 k-dimensional module elements together to get another k-dimensional module element. You could do like a dot product of them, but that would get you a single polynomial. But in any case, you can do addition, just component-wise addition, and that works out fine. You don't have to do anything fancy like with that's the same with ring LWE. The homomorphic addition is much easier there than the homomorphic multiplication. You don't have to worry about like using leveled stuff or powers of the secret key. For addition, everything works out very simply. You just do component-wise stuff, and it's all fine. All right, so in this case, we're adding together binary polynomials. Component-wise, I guess these are like the different coefficients of a polynomial, and then you're adding them together. And that's fine. All right, yeah, I think that's it. We're back. Okay.
Well done. Yeah, I am here. I remove myself from the stage, so you guys, you take the center. You are the stars of the show. So yeah, well done. Nice for the nice presentation. Let's look at. I think I'm actually surprised that it went more in depth than I was expecting. So well done for that, for both of you in your sections. So what I will do now, maybe I will let you guys, I have my own questions, but I let you guys look at the questions. Can you see the questions?
There's a bunch in the chat already.
yeah. If you want to address any of them, you can just highlight it. If you click on it, it will show up on the screen. And then if you want, you can read it, or you don't have to do that. You can just pick whichever. Some of them you might have already answered some of them on thing as you went along. For example, this question about distribution. Sorry, about the sampling thing.
Oh, how finding the secret key and distinguishing the public key from a uniform sample. This one.
Yeah, feel free to take any.
Yeah.
Yeah, I think it was answered. Yes, Shor's algorithm does let you break elliptic key cryptography. That one is vulnerable to quantum attacks.
I'm reading that one. Someone asked, does the Shor algorithm allow you to find the key for ECC? That's a good question. I think the answer is yes.
Yeah.
But I only know by analogy, right? Like in RSA, you're really just taking powers of m, right? It's like m to the e. And so like on an elliptic curve, it's the same kind of operation, right? It's just you have a base point p times n, right? And so like you're kind of doing the same thing. You're just using the operation in the group, which it just looks different, right? Because one is multiplication and one is addition, but it's like you're just taking this operation in the Abelian group and repeating it over and over again. So I don't know what the exact algorithm is, but it's basically that.
Yeah, it's certainly the same. It's certainly the same idea. It's the same sort of reasons why you can use a quantum algorithm to do it, even if the details are slightly different.
Yeah, because RSA is a little different because you are factoring an integer. I don't know if you also factor an integer in that one as well. I don't know.
No, you're not factoring in an integer, but sort of the same kind of thing. This discrete logarithm you can still solve using it.
Yeah.
Yeah, that's right. I think I wrote that as well on the thing.
Yeah.
It is because it's based on the discrete logarithm problem. This is also a problem that's subjected to the Shor's algorithm. I think the reason why this other ECC is not that because the problem is much more harder to describe. Factoring is much more simpler, so that's why most people are not aware of the underpinning problem that the ECC is based on, and also how Shor also actually the algorithm also breaks this as well. Yeah.
There's another one that says, what do you mean when you say the polynomial is insecure, though?
Oh, the x to the n minus 1?
Yeah, that's a good question. This basically...
You want to highlight it?
Yeah, that one.
Yeah, so I'll answer, and Thomas can probably answer a little better. But yeah, I mean, it has to do with how you factor it in the structure, I think. Like x to the n minus 1 is literally the ring of integers in a cyclotomic number field. And so x to the n minus 1 factors as a product of cyclotomic polynomials, and then those actually further factor modulo p. And I just think that the structure, there's too much structure, but I don't know the actual...
That's more or less the idea, yeah.
Yeah, I don't know the precise reason, like the precise attack, I should say.
Certainly anything involving roots of unity is extremely heavily studied in number theory, so it's not too surprising that people would have some way to attack it based on all of that information.
Yeah, I mean, I've looked at the factorization mod p of x to the n minus 1. It's interesting in its own right.
Yeah.
Useful if you're trying to do Fourier transforms over finite fields, but I have not looked at the factorization of x to the n plus 1, and I think it's less studied. I think if number theorists wanted to figure it out, they would have, but it sounds like cryptographers have just not found an attack on that particular version.
Yeah. I mean, not only is it less study, there is a lot less structure as well. So I think it's plausible that there's not actually some attack that people haven't bothered to find, but who knows?
Yeah, the structure of the ring of cyclotomic integers is like historic. I mean, I think Gauss studied that stuff, so it's been around for hundreds of years.
Yeah, but you never know those. There might be some clever person coming
for
up.
sure,
I
for sure,
remember
for sure. I'm not going to say that it's impossible.
Making grandiose claims, Thomas. So.
Yeah. No. This is cool. It's actually a good good point there. This is what makes cryptography interesting, because it's a cat and mouse thing. Mathematically things are hard, but it doesn't tell you that there are certain a lot of the interesting thing is it doesn't say actually, for example, that there isn't. All we know, there might be someone who possibly know there is a classical way of solving the factoring problem, but we don't. At least no one came forward.
They're probably in hiding somewhere. That would be.
Well, given the use cases, banking and all this type of stuff, I would also keep it secret, no?
It would be very secret. I'd be shocked. There's another question. Can we highlight them? It says, is it what they say?
You can just click on them.
I think we cannot. I think it might need to be Bombardier.
I think.
Okay.
Is it what they say about federated learning or something? Yeah. Okay, I'm just going to talk. Bombardier actually is a better person for this, but federated learning is a system used in machine learning which allows for a more distributed training of the models, is my understanding, so that you can train models locally at nodes in the network, and then you can send them back and sort of put the models, like assemble the models together, I think, into like a global model. I'm probably getting some stuff wrong, but
you're correct.
You're good. And in any case, this is an application of homomorphic encryption, I would say. I would say they're not the same thing, but I would say you can use homomorphic encryption in order to do learning while keeping security.
Yes, exactly. So the homomorphic encryption you would, I guess, when you're doing this, I think it's also called like privacy enhanced ML is another buzzword attached to that.
On this, actually, I will just share this because this is cool. Just to think how actually what you guys are saying about, homomorphic encryption can actually make federated learning more secure. Let me just share this, now that we have more time. Let's see. Just bear a second. That's why these privacy enhancing technologies are layered, on top of each other. They complement each other. We can also talk about differential privacy. Let's see, just a moment. Let's see. This wasn't planned, but I'm taking the opportunity because I'm to evangelize federated learning, but also homomorphic encryption. Let's see. So I'm going to use this overlay thing that we did with the Lord of the Ring. Let's see if you can see this for everybody there. Yeah, does it show up?
Yeah, it's covering us up, but that's okay.
Here's an example. I like this. So say for example, you have 3 hospitals. A, B, C. They want to train a common model. They have sensitive data they cannot share with each other. So this framework of federated learning is basically, you have the clients, train their model locally, and then they share the model parameters. This thing then is assembled by the aggregator, and then new model is built. Now, where does homomorphic encryption comes in here? For example, the model parameters can obviously provide a way of an attacker, there are some attacks that enables the reconstruction, some knowledge about the data in the clients just through the model parameters. So ideally, what you want is to encrypt the model parameters as well, and then the aggregation is done homomorphically. So this is where homomorphic encryption can add an extra layer of security into federated learning. So it's not like as it is always the case. It's not like you have to choose one versus the other. They actually have to work. They can work together in harmony. In this case, homomorphic encryption in complementing, adding extra security to the federated learning setup.
Cool. I see another question that I'm not going to be able to address, but I think I'll try. So it says from George Zipperlin, that's a little garbled. My question is, how do you do arithmetic in your ring on a machine, let's say 64-bit words?
Let's see the question. It's from George.
George
Gosh,
Zipperlin, it's like 3 down.
Okay, yeah, this one.
Yeah, that one. I'll say what we did because I'm not quite sure what do you mean by machine word length, because maybe you're talking about assembly code and talking about a register length or something like that. I mean, for us, we're a little simpler than that, I think is the answer. Like, we use the I64 integer type, the signed integer type in Rust. And our polynomials are essentially, they're like arrays of I64 integers. They're more like vectors of I64 type. And so when we do polynomial multiplication, we actually use a class called polynomial, capital P, in Rust. And so this does the multiplication, and that's the ring, right? And so we just have to do Q. So Q is the modulus. So we take our polynomials, we multiply them. Thomas wrote a faster algorithm to do the remainder. So you have to mod out by x to the n plus 1, which basically means substituting x to the n with -1, basically. And you can do that pretty quickly, but you're always using arrays of I64 type. And so, like, that's obviously, we talked about the multiplication with the number theoretic transform to speed it up. But as far as 64-bit words, the only other relevant thing I can think of is the way that we encode, which is different than encrypting, right? So, like, when we encode like literal words, we're typically using, I think, binary encodings. We're just breaking our Unicode characters into bytes and using a binary encoding, I think.
Yeah, that's why, like, we have this ciphertext modulus as something other than 2. I guess that's mostly just for like testing the homomorphic encryption. We're just using like 2 times 3 for the homomorphic multiplication in ring LWE. But really, we could just use the ciphertext modulus as 2 because we're encoding everything in binary anyway.
Yeah. So that, I think it's not exactly what you asked, but I tried to address it.
Yeah, you can always, George, follow up with anybody, in fact, who is attending here, and because they are also looking for possible contributors, for this for their project. So just follow up with them if you have any questions that they might not be able to address here.
Yeah.
I have do you have any other you want to select before I
the one right above that, the question about parameter selection, I guess we could talk about that a little bit.
How can we, okay, this one?
Yeah, that's right. Yeah, so this is for module LWE, so you're able to select both N and K. Yeah, so the thing is that the whole reason why you would do ring LWE as opposed to like standard LWE is because it is faster, because you have this extra structure of this polynomial ring as opposed to just like a generic vector space mod Q. And so you do want to do some amount of balancing between N and K. But if you're just making small changes to the security, you can fix N as some reasonable number and then hard code a bunch of parameters for the number theoretic transform, and then just adjust K a little bit up or down to increase your security. But you don't want to make like K super, super big and N really small, because then you're like going to be doing stuff pretty slowly, right? The module LW, the matrix part of the computations are a little bit slower than the polynomial part, I think.
Yeah, I mean, Thomas, you can correct me if I'm wrong, but I think I only recently read the original Kyber paper, and I think they were using like K equals 2 and K equals 3, so like really small values of K.
Yeah, you don't want it to be too big. Like we had it as 8 or whatever in the parameters we're using, which I think is reasonable.
Yeah.
This is also the thing with the cryptography, right? It's about trading off between the highest security possible, the practicality side of it, because you don't want to make something, okay, it's very secure, but it's impractical to run, right? It's very computationally expensive to do. So this is also another trade-off to the in terms of like practical implementations of these schemes.
Yeah. There's one question I'll answer with a non-answer. So it's from LinkedIn user. It says, "Do you please touch upon how come the study of representation theory suddenly lead into cryptography at some point?"
Someone asking about representation theory.
Well, just as he said, he mentioned it in the intro.
I mentioned it in the intro. It's 2:18 p.m. It's a little higher up.
Yeah, this was like the first question.
Yeah, it's under "Thank you" from Zeku Group.
Let's see.
It's also next to "Is ECC vulnerable similarly though?" Thanks.
Okay.
Well, I'll just answer it and see if Benbordy can highlight it. But
okay, this one. Yeah.
Basically, representation theory, to be honest, is pretty disjoint from this. I was, I guess, originally, I was doing some math research that involved representation theory, in particular of the symmetric group over finite fields, and it's kind of how I met Benbordy, actually. I was doing this research and I was studying this ring, like f sub q of x modulo x to the n minus 1, because I was studying sort of the representation theory of cyclic and symmetric groups over finite fields. And this ring just showed up, and it was like, I was like, oh, I had to study it and kind of get familiar with it. And then I think I somehow stumbled upon Zeku Group, and there was sort of the analogous endomorphism ring on there. So I was like, okay, that's interesting.
Ring is everywhere.
Yes, just like seeing the same ring, like a character coming in like off the side of the screen. I'm like, what is this ring doing here? And yeah, but I mean, representation theory. I mean, I don't know. I'm sure Thomas knows a bunch of representation theory, but we don't really use it that much.
Certainly not for this. No.
Not for this. So these rings, there's no like groups that we really need to represent here. I mean, the closest you get to representation theory is actually the number theoretic transform, because
that sounds right.
That is essentially the fast Fourier transform over finite fields. And the fast Fourier transform is all about the representation theory of a cyclic group, Z mod NZ.
Yeah.
So to answer your question, that's the only representation theory that shows up.
I actually recommend you looking at these papers, like this one. And there's another one on group action-based cryptography as well.
Yeah, I've thought that there was maybe some schemes analogous to NTRU using the group algebra of the symmetric group rather than the group algebra of a cyclic group, but it's that stuff is like just research.
Yeah, and as always, some emerging stuff in cryptography, it takes like years for people to actually, not just because of the standardization as well, because no one will use something that hasn't gone through, at least for practical application, that hasn't gone through, standards, Elliptic curve cryptography was invented like in the 80s or something, but it didn't
get used for a long time.
For a long time, correct. In fact, some people, when it first came out, people thought why would you use elliptic curves for doing cryptography and these things? So
it's interesting because it takes a while, and I think it takes a while for the community to really understand like deeply some of these things. Like even now, like even talks like this, I think are helping like introduce the community to like lattice-based cryptography, because it's pretty, you know, esoteric, and I mean it takes time for people to process it. It's taking time for me to learn it. It's taking
Yeah,
time
for sure.
Yeah.
So
Yeah, and the beauty of it also, you know, is like the ring LWE, you know, is because of it's a hard problem. You basically get post quantumness for free as well. So, you know, or at least no one. There was a paper. There was a Chinese researcher who published a paper saying that he found an algorithm for, but soon some cryptographers went through and they found some loopholes in the proof. So it still stands.
yeah, cryptography. It's interesting. I don't know this side as much, but there's the attacks on some of these systems are really brilliant. You know, the way that people break these crypto schemes. I mean, it's like scary how good they are at breaking things. So like Bambordi was saying, with a new idea or research idea for a crypto scheme, I mean, it has to withstand.
Yeah, it's got to stand the test of time for a bit, for sure.
Yeah, because it's like too easy to come up with a scheme, and then it's too easy to have someone just break it immediately.
Yeah, that's especially when you have very talented mathematicians like you guys, you know, coming up with clever mathematical attacks that are feasible to implement and break. And, you know, the intelligence agencies are full of this, right?
Yeah.
Well, yeah, and when I talk to people who are sort of white hat hacker people, I mean, yeah, they're constantly looking for vulnerabilities and exploits, and it's not always like the most sophisticated stuff, but it's like anything that you didn't think about, like they're thinking about, and it's very impressive.
I mean, like, a big part of the problem is like it's impossible to prove that something's secure. Like the best you can do is say like, well, I can reduce this to this other problem that we think is hard, but like actually proving that you can't solve something is that part of theoretical computer science, like it's super difficult.
Yeah, which is why transparency is key. You know, no one, you know, if you say you have a very secure cryptography, but you don't want to share with the world, that's definitely not secure.
Yeah, it's more secure if the development is out in the open, because then
exactly.
It'll get challenged.
So it has to be, everything has to be open.
And you can see that people haven't completed something.
Yeah, I mean, quantum algorithms for NP hard problems is definitely would be quite impressive from anyone who's, you know, outside the I guess like it's just very hard to do that. So it's nice when these cryptography schemes are based on NP hard problems. I mean, I'm surprised RSA just lasted so long. It's not even clear if there's a polynomial time algorithm for integer factorization, and it's like managed to survive.
Yeah, very few things. Eventually, you know, people will find, which is good. You know, we shouldn't hate the white hackers or the crypto-analysis people, you know, because they are part of the ecosystem to make the security, you know. So, you know, like I remember this thing of speaking about post-quantum, Psych was broken by, you know, they were using some very obscure technique in algebraic geometry, and with a laptop, that's it. It was broken.
Yeah, that's amazing. I mean, yeah, that's what's like a little surprising. Like it's a balance between like structure and lack of structure. You know, it's like if you have a lot of structure with the elliptic curves and the isogenies, like that's great, but then that's exactly what people use to exploit stuff.
Yeah.
I think nowadays people have, I think in the past 10 years, people have started to embrace randomness a lot more than,
I mean, like learning with errors just straight up is just like very inherently random.
Yeah, and randomness is hard to beat. I mean, what's interesting about randomness is it's not actually random. I mean, that part, you know, like should be noted, but it's still, even pseudo randomness is pretty.
This is actually very interesting because there are some people thinking about, as you put it, you know, anything that a human generates, you know, that we generate an algorithm is definitely not random. You know, what if we let nature generate randomness? So if,
Sure.
for example, the 10 quantum computers, for instance,
Well,
like,
quantum randomness is very random. Even
yeah.
our random
So-
number generator is from, they call it from entropy. So it's in Rust, it uses the system entropy actually to generate random numbers. So that's pretty close to nature. I mean, I don't know exactly how that pseudo random number generator works, but if it really is coming from the entropy of the machine, I mean, that's cool.
Yeah, so this brings me to my other question. I don't know if you have any other that you want to select from the audience before I
think
ask
we've got
mine.
pretty much all of them. Yeah.
Yeah.
Okay. The first one is on the implementation side. Why did you? I know this is like a thing. Why did you pick Rust, for example? Was it because there are a lot of projects that you saw, especially emerging in cryptography, that were also using
a lot
Rust?
of applied cryptographers use Rust. That is definitely true. And I think it's because it's a lower level language. There's probably some more reasons.
Yeah, I mean, you could use C++ and C. Rust is just kind of like, it's a little trendy, but it does seem that it's a trend amongst, yes, cryptographers. And there's one person in particular who wrote some very well-known elliptic curve cryptography stuff, and they did it in Rust in 2017, which is right, like, that was a while ago when it was just coming out. And I think the language has matured quite a bit. I actually happened to take like an applied Rust course from Duke like last year in May before all this. So this just kind of worked out. I think I was anxious. I thought it would be cool to try this language out. And I mean, I should learn more about what is actually meant by memory safety, though. Like,
Rust is more memory safe. Yeah, that's what I heard too.
I repeat that a lot, like a parrot, but I don't know like what I'm actually saying other than, it, when you use it, it like forces you to not move things, and it forces you to use references, and it
That's probably what it means, maybe, at least in part.
It's like a
constraint
cop. Yeah, just like it's like constantly watching you to make sure you don't, move a variable from here to there. So I don't know. I get it when I use it. I feel like it's very tight. Like it just feels very. I don't know. Like the warnings are really good. It's very like verbose when things are wrong. So like when it's working, you're just like, yeah, I have so much confidence that this program will run. I don't know if the output will be right, but the program, it's almost like a self-checking system. It's like very, I don't know. It feels a little bit different than writing. Definitely feels different than Python, and it feels different than C++ too. But I'm shocked that C++ hasn't just copied the best features from Rust. Like honestly, because that language is used by a lot of people.
Yeah, sometimes these legacy languages, well, I'm saying legacy because they're being around longer, they tend to be very thing in terms of learning or like copying, or not copying, like inspiring from the new thing. I guess also is because of the design, also the way they were designed. Maybe it makes it harder for the thing to just move over to as opposed to something that's designed, something new.
Yeah, I mean, I think George Zipperlin made a good point. Like C++ is more explicit with like you have to like use malloc and allocate memory, and you have to free memory. And Rust doesn't have a garbage collector, but we didn't have to use either of those. Like we just were, the memory seems to be managed in a better way.
Mm-hmm.
It also shows how the industry, the thing evolved, nowadays, especially with these abstractions built over, the thing that, maybe a developer, someone who used to write code like in the 80s or something, would have to do a lot more than nowadays, where there is obviously more abstraction, where you don't need to think a lot in too many details, basically.
Yeah, I mean, it's cool, I think, to work at a low level sometimes because, I don't know. It's just everything's more explicit and more, yeah, like in Python or like in like let's say in Sage, when you write this code, it's actually a lot like shorter. Like it's very
Well,
short.
yeah, that's the whole point of it being a higher level language, right?
Yeah, you just import everything. You're like, but if you're writing in Rust, I mean, you have to like kind of like you almost have to like implement like a field, like a finite field, because you're like, okay, there's just it doesn't exist. And honestly, uh, yeah, we had an experience when we were writing the number theoretic transform, and Thomas and I were talking, and I was like, oh, can we just import this? You know, like it's, and it didn't quite exist. I forget if we told you to import it, but there were like a handful of number theoretic transforms, but the best one was from Zama, and we looked at it. It's called like Concrete NTT, and we looked at it, and it's very complicated. I mean, it's like a lot. It's written in a very like structured way with like taking into account of like 16-bit, 32-bit, 64-bit. I mean, it's really detailed. But one of the cool parts about Rust was that we just wrote our own number theoretic transform and then published it as a crate, so now other people can.
Yeah, I mean, I'm sure our crate is much worse than theirs, but
Ours
it
is
was
much
nice
worse.
to be able to do it ourselves. I think we learned more doing it that way.
Yeah, but I mean, it works. It does
It
the
works.
NTT, and it's fast.
This
and
is actually
it's
a very good, yeah. It's a very good thing. We always, advise the young programmers, for example, coming in nowadays. It seems to be popular to just use frameworks that do things already. Speaking about this high level stuff, but going through details like you guys you've done, this is actually gives you a lot of. It's pain, it's painful, but you also get to really feel, and also the freedom that it gives you to do something from scratch as opposed to just using some framework and you forget about it. Yeah. So definitely it's definitely a recommended, especially if you are starting a new project, right?
yeah.
You also have more freedom. You
I
don't
like the
depend
freedom.
on the thing. Yeah.
Yeah, it's like when as we're building this, it's kind of nice that we have our own GitHub organization or just a set of repositories, and if we need a tool, we can import it if one exists, but we can also write it ourselves and kind of slowly build up a really cool library of Rust tools for cryptography. And I think if those tools are really good and really well written, then other people will use them. And I notice, there are other applied cryptographers that are very, very advanced, and I'm kind of keeping an eye on it. But the space is pretty new. There was someone, I won't name him, but he published a constant time implementation of finite fields yesterday, and I was like, that's cool, and it's new, and so I think as we go forward, we're gonna want to write our code in constant time at some point, and that's the only thing that like worries me, because it's not easy to do that, and I think, but we will, in order for the code to be like usable in the real world, it has to be constant time.
Right. Otherwise, there's timing-based attacks.
Yes, there's timing-based attacks and other things people can do, and so it'll be interesting going forward to see which route we take and how much we can import from other people and how much we write ourselves. But hopefully it'll be good to get out into the ecosystem a little bit and see what we can contribute. And but yeah, I mean, it's nice that we have some functional code at this point. I think
Okay, this is actually a nice segue. Yeah, sorry, go ahead.
No, I was just gonna talk about next steps, but we could talk about that later.
Yeah, no, that's exactly what I was going to ask. Indeed, what's the next step, and also if somebody wants to help, contribute, into your project to mature it, to take it,
so
how would they go about?
Yeah, I have a couple next steps, and Thomas can correct me or suggest other. But just on the top of my head, writing stuff in constant time is a big one. So that would be on the list. The other thing that's on the list is right now we have ring LWE and module LWE, but what I've wanted to do is to bring this to the NIST standard. And so to basically have that be a goal and to say, can we write, so the next most obvious thing that I don't think would be that hard would be to write a KEM. So to write a key encapsulation mechanism in Rust, which would basically be like module LWE, but the next step, which would be to do a KEM, and we can model that on the Python code that Giacomo Pope has written, which already exists. Doesn't have to be the exact same, but I mean, that's in Python. And so we could potentially, do a Rust version, maybe in parallel with trying to get some of this constant time stuff done. But those are the two things that are on my mind.
Yeah, I mean, we have some like small efficiency improvements to make, especially in module LWE. Like we don't have the number theoretic transform implemented there yet. Yes. And also like the matrix multiplication. We just have a super naive algorithm and we could use something a lot better.
Yeah, so I mean, we try to track these as issues. And so I will add those two issues that Thomas mentioned. So just in GitHub, there'll be issues. So I'm going to try to make them as inviting as possible to outside collaborators. Like if they see an issue and they're interested in working on it, like send me an email, send Thomas an email, or send the email that we have listed that's very long on the repository that we need to change. But yeah, there's email someone and or just respond to the issue and say that you want to work on it. And I'm like very happy to collaborate. There's some low-hanging fruit.
Maybe speak to you guys first before they submit anything.
Yeah, well, we may have to put in some like, the usual GitHub sort of checks and balances that are in there. But you do have to make a pull request before merging. And I think only Thomas and I can merge at this point. So, it's top down.
Yeah.
But yeah, collaborators.
It is how it should be.
Yeah.
Finally, my other question, this is more from like, what sort of advice would you give, because obviously you guys, you have now gone through this thing from pure mathematics being on the thing to now looking at practical stuff in industry and this thing. What sort of advice you would give to someone, say a PhD student in a maths department somewhere, maybe doing representation theory or possibly something to do more direct with the cryptography stuff? What sort of advice would you give them? The key from your own learning experience and this type of stuff.
I would say definitely engage with industry and the real world a little earlier and I think I had a chip on my shoulder about the like industry and the real world. Like, I don't know, I just thought all the cool stuff was happening in academia and like, postdoc to professor to research was like the only way. And I've just seen a lot of really interesting problems in industry and a lot of really brilliant people and just the world is an interesting place. There's a lot of mathematics in it. And I was surprised learning this cryptography was really enlightening because as I learned more about lattice-based cryptography, I was like, I had learned a bunch of number theory in graduate school, like early on, like the purest math you could learn, like really, algebraic geometry, just like Iwasawa theory. I mean, really abstract stuff, category theory. I mean, and then like when I started to learn about ring LWE and module LWE, I was like, oh wow, that like these objects are very number theoretic, and you can use like all of these tools in your toolbox, but like cryptography in the real world is really interesting. It's just I'm more fascinated by that aspect now of like these are real computers in the real world and real messages that are really secured and there's like it's driven by pure mathematics at its core. And I don't know, I think, and then also just write code, like write code all the time.
Yeah. This project's been really good.
Yeah. Well, yeah, I'll hand it over to Thomas.
Yeah. I agree. Definitely like doing more code earlier would have been a lot better. And like, yeah, just like if you're trying to learn something, just like getting your hands dirty and doing a project like this is a really good idea. And also, yeah, they're like, if you're at grad school, there are probably a lot of opportunities to like get involved in this kind of stuff, even as a pure mathematician. Like we definitely had some like seminars about like cryptography and more other things, more applied stuff associated with industry that you can just like show up to. And I did a few times, but like, yeah, you can do that a lot more.
It doesn't give you that taste, that thing, then actually you going and starting a project and actually
yeah,
looking
for
what
sure.
other
Yeah, just
doing,
like
right?
going and doing a project yourself is an excellent way to learn this kind of stuff.
Yeah,
Yeah.
I would caution, I would say, because I did a lot of personal projects to like learn coding and to become a programmer. And I would say that that's great. But I also think that if you can find open source projects and people to work with, it's a lot better than just publishing your own GitHub repositories, because it's great, but it's not the same. It's not the same as like being an open source project and having people review your code and having code basically pushed to production, right? Because that's to get from an academic to an industry level, you want to be writing production code, and the way to learn how to write production code is like in an open source project, and those communities are welcoming, especially to academics. I contribute to Sage Math, and that's an awesome way to transition to, because whatever math you're interested in, I can guarantee you, I can almost guarantee you that it's in Sage, or like a lot of it is, or if it's not, that you could potentially just implement it in Sage. Like it's not maybe the most high level quantum field theory, there's limits, but it's still like it's all there and it's in code. And I've been able to do math research and collaborate with people who also contribute to Sage Math, and I've had some really nice collaborations, particularly with someone in Japan, and we've gotten some really cool stuff done, and then it's implemented, and then it's very concrete at that point, and we're writing a paper as well. But I think, I mean, to transition to industry, I think writing code is really important. I mean, it's like it's hard to avoid that, even if you're a mathematician. It's like you want to be able to translate, like in academia you translate your ideas into papers, like in the real world translate your ideas into code.
No, I completely agree. It's always helpful, if you have an idea and then implement something that you can show to your colleagues and the rest of whatever the company that you are at, to think this is what really makes the difference as well for companies, so yeah, definitely I think it's something. And as you put it, Jackson, and you guys, you don't have to start from like zero, right? There are already a lot of things that you can that can help you to get started really in this front. As a mathematician, you already have the math stuff. This is definitely something that you are one of the few in the world coming from your field, so that's definitely a plus. But then the other thing, having this practical thing of implementing stuff is definitely very helpful. It's a plus. Okay, I don't want to drag you guys too, because it's been like a very, very long session. Actually, time went so fast. It actually shows like how interesting the session was, right? Because we are all awake.
Thanks. I don't know where you are in the world, Bamborde, but thanks for coming at this time.
So anyone wants to say anything? Any last question you want? Anything you want to ask before we close? And before we say thank you to our guests, our special guests, for the amazing presentation, amazing talk. No? Okay. Maybe we can leave it here. So thank you so much again for joining us, and thank you, Thomas and Jackson, for taking your time, and well done, for the project, and for everyone in the community, please follow up with them if you have any questions about the project, or you looking possibly to contribute something. But it's been really, really, really great. I hope you had some good taste of lattice-based cryptography, and in particular, the application to it to homomorphic encryption. So, I hope it was like a 2-for-1 thing. You came in not just to see a demo, but also to learn something that these guys have been working on. So yeah, so thank you, everyone. I'm going to stop the stream now, and you guys, I will stick with you on the backstage for a few minutes. So to everyone else, thank you so much for joining. And by the way, Jackson, we will be having a course on homomorphic encryption and post-quantum cryptography. So stay tuned for that. Both Jackson and Thomas you'll catch up with them again. So have a good day, and I mean good weekend. I actually forgot it's Friday, so yeah.
Cool.
Have a
Thank
nice
you,
weekend
everyone.
wherever you are. Yeah.
Thanks.
See you. Bye. I'm gonna end this stream now. And